Now let's talk about what to do when integration by parts doesn't work. Here's an example. Let's find the integral of 2x sine of x dx. Now, we've already solved a problem similar to this in a previous video, so we already know that you can use integration by parts to solve this problem. But what happens if you make the wrong choice for your u and dv? Here's our formula again. The integral of u dv equals uv minus the integral of v du. Always good to write that formula down somewhere so you remember what you're aiming for. We want to break up our integrand as a product of these two things, u and dv. Now, in other examples, we've used the x or the 2x as the u. What happens if you use the sine x as the u instead? If you use sine x for your u, you'll have to use 2x dx, everything that remains, for your dv. Now let's try and see what happens if we do this. We'll have to differentiate our u and get du. That's going to be cosine of x dx. And we'll have to find the antiderivative of dv, which is v, and that gives us x squared. And now we'll put these together. This integral equals u times v, that is x squared sine of x, minus the integral of v du, which is x squared cosine of x dx. Uh-oh, this didn't work because our integrand is now more complicated than it was when we started. As we know, sometimes the integration by parts process doesn't instantly give us an integral that we can solve, but it should give us an integral that is simpler than the integral we started with, except in the case of those cyclic integration by parts, where we end up with an integral that is basically the same structure as what we started with. This time it's more complicated. We have an x squared here instead of the x that we had originally. So what this tells us is we have made the wrong choice for u and v. And we should back up, start over again, and let's just make a different choice for u and v and try over again. This time, let's try and let our u be 2x and our dv be sine x dx. So our du is 2 dx, the derivative of 2x, and our v is negative cosine of x. And now we just need to put these together into our formula. So our original integral equals u times v, that's negative 2x cosine x, minus the integral of v du. Now our v is negative cosine x, so I can bring that negative out and make this plus cosine x. And our du is 2 dx. I'll put the 2 out in front and the dx here. And this is easy to solve then. This is equal to negative 2x cosine x plus 2 times the antiderivative of cosine x, which is sine x, plus a constant. And we're done. So this means if you think that integration by parts is a good choice, and you try some choice of breaking down your integrand into a u and a dv, just try it, see what happens, and the worst that happens is you end up with an integral that is more complicated than the original, and you go back to the drawing board. There's no harm in trying it. And what you'll probably want to do if that happens is swap your u with your dv and try again. Hopefully you will end up with a new integral that is easier to solve, not harder to solve. Now let's try another example. Let's find the integral of 3x e to the x squared dx. So, as we've done before, we've done problems similar to this, where we have an x being multiplied by an exponential function. And we have tried integration by parts. So let's try integration by parts here. Let's pick our u and our dv. Last time we tried this, we used the algebraic or polynomial part for our u. So let's put 3x as our u. And for our dv, we'll put e to the x squared dx. Now we'll differentiate our u. Du equals 3 dx. That was easy. And we'll need to find the antiderivative of v. What is the antiderivative of e to the x squared? Well, we don't know. So this does not work. Because we can't integrate e to the x squared. We can't find v. So what do? Well, the last time that our choice of u and dv didn't work, we tried again. Let's try again. This time, let's let the u be the exponential part. We don't know how to find its antiderivative, but we do know how to find the derivative, so let's do that. Our u is e to the x squared, and that means our dv is whatever's left over, which is 3x dx. The derivative of u is du. We'll have to use the chain rule for this. That's going to be e to the x squared times the derivative of x squared, which is 2x dx. And our v, we'll find the antiderivative of 3x. That's going to be 3/2 x squared. Put that all together. Our integral equals u times v, which is 3/2 x squared e to the x squared, minus the integral of v du, or v is 3/2 x squared, and our du is, let's put the 2x first, times 2x e to the x squared dx. Now we can simplify this bit. To save space here, let me just cross out all this. That 3/2 is really, times 2 is really 3, and x squared times x is x cubed. So we actually have the integral of 3x cubed e to the x squared dx. Well, that made it worse. This time we were able to do the integration by parts. We were able to break the function down and get a u and a dv and figure out what du and what v are. But we ended up with an integral that is more complicated than we started with because it has an x cubed in it, and the last integral just had an x in it. So this is worse. So neither choice of our u and our dv is actually going to work here. Now you might make some other attempts, such as using that constant as one of the two pieces and the x e to the x squared, lump that together, but that's probably going to be even more complicated than you want. Let's try something different. Let's back up. Let's back up and think about what our first line of attack should be in any integral problem. Before we try integration by parts, there's always a different technique we should think about first. And you really should always try this first. The technique is u substitution. You should always try u substitution first, because you'll know right away if it's not going to work. And even if it doesn't completely solve the problem for you, it may give you a simplified version of the problem. Oftentimes, u substitution will be the first step of a multi-step process. So let's try that first. Now be careful here, because we do use the letter u in both of these techniques, but we're using the u in two different ways in these two different techniques, so watch out. When we do a u substitution, the usual logical choice for u is whatever function is being plugged into some other function. So normally, if we have an exponential function, it will just be e to the x. But instead, where there should be an x, there is a different function. There is x squared. So that's a good choice for our u. U is x squared. And if you think about this for a little bit, you'll realize that this is definitely going to work. And the reason is because the derivative of our u is showing up being multiplied by the rest of the integrand. The derivative of our u is 2x. Now, constant multiples we never need to worry about. The important part of that is the x, and here is the x right here. So our du is 2x dx. Don't worry about those constants. We can easily just divide both sides by 2 here. And the x dx is showing up in our integrand. So we're ready to do the substitution. This integral equals the integral of, keep a 3 there. The x is going to go away. We're going to have e to the u, because x squared is equal to u. And the x times dx gives us our du over 2. I'm going to put the over 2 here so that I keep my constants all together. You could pull that 3/2 out if you want to, but it's hardly worth it because we just have a number times e to the u du. That's easy to integrate. And our integral becomes 3/2 e to the u plus a constant. And of course, we should never leave our answer in terms of a variable that we didn't start with. We should always put the x back in. Our u is equal to x squared, so we have 3/2 e to the x squared plus c. Now, if you're experienced enough with u substitution, you may have realized right away that we could have used a u sub for this problem before we even tried to do integration by parts. That's a good instinct to develop, and you should always be watching out for how can I use a u sub before you try integration by parts. Usually it will go in that order. So if you're trying integration by parts and it's not working, a u substitution is a thing to go back and consider. But ideally, you'd consider it first, and it would help you solve the problem or at least simplify the integrand before you go into any other techniques.